Hello, welcome to your lesson on the area of a triangle and the sine rule. You're going to need your calculator for this, and again, make sure you're in degree mode. Every time we do trigonometry, we're going to use degree mode for the time being. Let's talk about a very big idea in the world of trigonometry. So first of all, we began with right triangles. In right triangle trigonometry, we could use it to solve parts of right triangles, but many geometry problems involve non-right triangles. For example, this triangle, we can see it's not a right triangle, but we do know some angles and a side. It turns out that in this triangle, we can use some trigonometry to help us find missing parts, although it's not exactly the trigonometry we know. So let's take a look at area first. Looking at these triangles, can we find the area of these triangles? In this first one, can we? Yeah, for sure. We can use the area of a triangle formula, half times base times height. In the second one, it's also a right triangle here we can see, so we can use half times base times height again. In this one, although the entire triangle is not a right triangle, we have this height line here, so we can use half times base times height. However, we don't know the height here, so we can use some of our trig knowledge to find the height. We could call that x, and this part here 24 minus x, because the whole length is 24. We can continue by doing Pythagorean theorem, x squared plus h squared equals 10 squared, and then making another equation that looks like this, Pythagorean theorem in this one. And eventually we have two equations with x and h, so we can solve for h. So it'll take a little work, but we'll get the h and we can find the area of that triangle. However, in this triangle, we're kind of stuck. We don't have a height line, we don't have another angle, we don't know enough, it seems. But it turns out we might know enough, so let's take a look. So here's how this one works. Let's begin with the area of a triangle. And make sure to write these notes. We're going to derive a new formula for area of a triangle here. So we have the basic area of a triangle, half times base times height. We're going to draw a height line here, called h. Notice in this triangle, let me go back before we had the h, we have angle A and across from it angle side little a, all right, angle B and then side B, and angle C and across from it angle side C. So that's usually how these triangles are labeled. You'll see these ABCs a lot in the next little while. Okay, so we draw the height line. Then we're going to use sine in each of these two triangles we've created. So in this triangle, sine of A is opposite of a hypotenuse, h over b. All right, and you can go on and solve that for h by multiplying by b. So now we have an equation for h. Now let's look at this triangle, and well, sorry, we don't need to go further with this one at all. We have h now, and that's all we need in this formula. So we can replace the h with what we found out h is. It's b sine a. So now we have this new kind of equation for area of a triangle, which does not depend on the h, it depends on knowing one of the angles. So that formula is half bc times sine a. Notice in the formula, we could have, instead of using sine of A, we could have done sine of B also and gotten a slightly different formula, or we could have used sine of C and gotten a slightly different formula. So this formula comes in three forms, so don't think this is the only one, but the point is that you always have two sides and then the other angle here. So you always have to know two sides and then the angle in between them, because that's what that is. We have B, C, and then angle A, and you can have it as a combination of any two sides in an angle. That will give you the area of a triangle. Let's try that formula here. So here's a simple situation. We have exactly what I said we just need. We have two sides and the angle between them. So we can use that formula. Let's try. Okay, so here's the area. Using that formula, we can find the area of that triangle like this. It's nice to have a formula like this because often we don't know the height and we do know angles. So check your work, looks pretty good. Okay, so let's move on from area. That's a simple formula. Let's go on to now talk about sides and angles. In this right triangle here, we know we could use trigonometry, sine, cosine, tangent, and we could find other missing sides like the hypotenuse or other angles. Okay, that's with sine, cosine, tangent help us with right triangles. But what if we have a triangle like this that's not a right triangle? Can we still use sine, for example, to help us find missing parts? Well, that's what we're going to do next. So let's say we have this triangle here. Is this a right triangle? If somebody told you solve for side B, how would you do it? Well, it is a right triangle, so you could do tangent of 32, for example, opposite over adjacent, and then you can go on to solve B like this. Okay, so that's a right triangle, so that's easy if somebody asks you to solve a side. But what about this triangle? Let's solve for B here. Well, hopefully you didn't get trapped into using tan again, because this is not a right triangle. Even though this angle looks like it might be a right angle, we don't know. So not a right triangle necessarily, so we don't know how to proceed. So let's check. It all begins with drawing the height line again. So let's do the derivation here. So here's this triangle. We're going to draw the height line, call it h. We're going to do sine of 40, so we're looking at this triangle, opposite over hypotenuse, and we'll also change that to h equals this, so multiply by 8. Now let's look at the other little triangle and do sine of angle b, which we don't know, but we can write that, equals h over 10. Okay, and that can, now that we have that, and we're looking for angle B, we also know h is this from the other equation we set up. So we're going to do some substitution here. Substitute for h with this, and we can solve for b like that. Okay, I don't think I went further here, but you can solve for b now. You can solve for it without using the height, and without having a right triangle to begin, right? So let's take that and make it a general rule. So in this one, if we drew a height line, we can say we have sine of angle C is h over b. Change that to h equals b sine c. And we can also do sine of angle b equals h over c. So we've created two equations using sine where we have common variable of h. So that one can be substituted in, just like we did here. We can substitute b sine c for h. And now we have an equation that's not dependent on h anymore. So we could have this triangle without h. It's an equation that just uses angles and sides. That equation can be rearranged like this. If you put the b under there, you end up with something like this. This is called the sine rule. It's a very important rule. It's a rule that allows us to find pieces of triangles without knowing that it's a right triangle. So it just connects angles and sides using sine. That rule can be broadened even further, that we had just two parts equal like this, but you can say that sine of any angle over its opposite side is equal to sine of any other angle over its opposite side. So we can write it anyway. The main thing to remember is you always do sine of an angle over its opposite side equals sine of an angle over its opposite side. So it allows us to solve for parts of triangles when they are not right triangles. It can also be written like this. You can flip all the fractions. It means the same thing. Or the main thing to remember is even though the rule is given as three parts here, it's not usual to write it as three parts. You usually just write it as two fractions. So like, for example, these two fractions are equal, or these two are equal to each other, or this one's equal to this one. Because when you write all three, there's just too many parts. You usually don't need that much. So again, main thing to remember, you're going to have sine of one angle over its opposite side equal to sine of another angle over its opposite side. That's how the sine rule works. Let's try it. So we have a triangle here. We're told it's triangle ABC. We know an angle, we know another angle, and we know a side. Let's see if we can draw it and find the length of BC using the sine rule. Okay, now that you've tried, let's check. So here's triangle ABC. We are given angles A is 65, angle B is 30, and side C is this one. So it's opposite angle C, and it ends up being the side between these two. So can we make the sine rule? Remember, for sine rule, we're just looking for things we know that are opposite each other. Well, we know angle, we know we're looking for BC. No, what am I doing here? Where's BC? BC is here, but we know this side. So I'm looking at this side and saying, do I know the angle opposite it? Well, I don't, but in a triangle, we do know the three angles make 180. So we can subtract those two from 180 and get 85. So we do know this side and this angle across from each other. And then we're looking for BC, so we do know this angle and we're looking for this side. So here's the crisscross I made here for the things we know across from each other or the things we're looking for. So writing a sine rule from that, we have A over sine 65 equals 13 over sine 85, right? The side across from its angle. That gives us only one unknown, so therefore we can solve. We have A equals 13 times sine 65. You punch all that into your calculator in one step, and you get an answer for A. I don't think I put the answer there, but we can get to the answer like that. Okay, so try these two. You're ready for another one. Try this one first. Okay, so you're looking for side BC. You look at that, you say, I know that angle and that side. I know that angle, I'm looking for that side. Set up your sine rule and put things in and solve. Hopefully that one worked out. Next one. This one we're going to look for an angle. Okay, just looking for an angle. So again, looking for things across from each other, we know those. We're looking for angle C and we know that side, so we go like that. Create the sine rule, and since we're looking for an angle here, make sure in the end you're going to use an inverse sine, right? Because to find an angle, we're going to do inverse sine. So check your work here. Plug everything into the sine rule. In the end, we need angle C, so we do an inverse sine of all of that, and we get this angle. Okay, that's the basics of the sine rule. You're ready to apply it. Let's take a look here. So here we have a diagram and a situation. Let's see if you can solve that. Now let's check our work. So we were looking for the length of the bridge, which is from A to C. But we do know this side. Do we know this angle? No, but we can find it. We know this angle because we know the other two angles, so we can find this angle. And then we have this angle and we're looking for this side. So again, begin by finding that missing angle, which is 20, angle C is 20, and then set up the sine rule and solve. Okay, next one, try this one. This one's a little different. Let's see if you can figure it out. Okay, here we have this side, so we can go like that, say, well, okay, if we know that angle, we can figure out that angle again. And then what's the other side we're looking for? Well, the question's asking for the distance from the boat to the shore. So is that AC? Is that BC? Well, it's neither. It turns out it's neither. The distance is always considered a perpendicular distance. When we say distance from a point to a line, it's always perpendicular. So the distance would be measured as a straight line that's perpendicular to the shore. So that's the one we need. But that one we can find after finding one of these two. Okay, so let's start by finding one of those two. So it looks like to set it up, we can find angle C is 73. Set up the sine rule, and this time the sine rule was set up for BC using 65, but it could have been for AC also, okay? It's either way. But anyway, we solve for BC here, we got it. Now that we know the length of BC and we draw this distance line, we can use simple trig in here to find that distance, and a sine rule was set up to find that. Sorry, just a basic sine ratio. Okay, check your work carefully there. And now let's try one more. It's going to be one of these ones with bearings. So we have port A and port B, which are directly due north of one another. Or sorry, port A is directly due north of port B. Tells you some more information. See if you can draw that diagram and solve. Okay, so let's take a look. Here's the diagram. Port A directly due north of B, so we put them like that. They are 15.2 miles apart. And we know the boat, which is here, is at a bearing of 120 from port A. So remember, for bearings, we start at north, we spin 120 degrees, we get to the line connecting to this, where the ship is. And the ship is at a bearing of 42 from port B. So again, we start at north, we spin 42 degrees, and we get this line. So that allows you to create this triangle. In this triangle, we know 120 out here, therefore inside must be 60. Because this makes 180. We know this angle, so now we have enough information. The question was, how far is it from each port? So we need AS and we need SB, and we can find them like this. Okay, so we set up sine rule a few times. We do sine rule to find this one, we do sine rule to find this one, and doing the separate sine rules, you can find the answers here. Check the work carefully there. This one was a little bit different. Okay. Let's end there. I'm going to show you the next thing in a quick video following this. So let's end this one for here and know that there's one other video coming up, and the other one is much shorter, but do watch it now. It's the next part to this situation.